Okay. Welcome, EE225E. Spin echoes. Woo! Spin echo. Who already went through the lab? Raise your digital hand. Okay. Any comments? If you have any comments for us, please, either shoot us an email or, please come to office hours. Me and Anita had a pretty fun office hours today, but still pretty lonely for office hours. Feels more like
11.
Yeah, feels more like EE16B kind of office hours where I usually, when I have 1,000 students, then it's just inversely proportional to the number of students that I have people in office hours. So the more there are students in the class, then the less I have. I think Ekin is probably a wonderful TA, so that's why nobody wants to come to my office hours, I guess. It's kind of disappointing. I can make her work a little bit harder so she doesn't have time and she becomes like more. No, shouldn't do that. Okay. All right. Well, so where were we? Remember where were we? I don't even remember. That was like ages ago. At least last week. What we're talking about?
I think echo is where we ended, if I remember correctly.
What did you say?
Echo.
Echo.
Oh, haha, echo.
Echo. That's right. Yeah, echo. That's right. That's exactly what we were. And we actually talked about in particular Hahn echoes, or spin echoes, right?
Hey, Mickey.
Yeah.
Don't you think it's odd that he figured this out with 290s? Because you'd think you'd really not have a lot of signal with 290s, right?
Actually, you have half. It's pretty high. It's not full refocusing, but it refocuses half of the magnetization.
Why? Why half?
It comes out. You actually derive it, so it comes down to be half of magnetization. There's actually a homework question about that.
Okay.
But we will go over it today. So the most that you get is with a 180, half of a 90, and then less and less as you get lower flip angle. But you still get spin echoes even at very low flip angles, which is interesting. So basically, yeah, it pretty much is an experimental discovery where, Erwin Hahn applied. There was a 90 here, and then there was a 180 here. And you look at the distance between here and here, and then if you look at the same amount of time after the 180, then suddenly there's this rise of signal at this point, which you don't expect. That was an unexpected result. And in order to understand, why is that, is because that's basically the spin echo, and this is kind of what we're going to go over today. Okay. And you've probably seen this in the lab, like in the lab, you implemented this. and you saw, it's like, oh my God, there's some signal that rises up, right? So it's pretty miraculous, I think, in some ways. In some way it isn't, once you kind of realize what's going on. Okay, and today we're going to try to do a spin echo on Zoom. I don't know if it's going to work, but we'll try. So here's a spin echo pulse sequence, right? So here's the idea. You put a 90, and then you put a 180, and a 90, the 180 is tau times after the 90, and then we should expect then what's called a spin echo to occur at 2 tau. Okay. And so once you excite, magnetization starts behaving like, exhibiting T2 star decay, right? There's basically starts losing coherence based on magnetic field inhomogeneity. And in addition to this, of course, is the natural T2 decay, right? That we're used to. So T2 prime and T2. Together, they create T2 star. So there's a decay of signal. And so once we excite, then you got all of those isochromats starts dispersing. And then once we get to the 180, the whole pancake, the pancake of spins that are now spreading up is being flipped. Now, if you remember, let me just play it again. The red spins are spins that go clockwise. So they're, I guess, faster spins, like higher frequency, whereas the blue spins are spins that are lower frequency. Okay, so they all end up with a certain phase, and once they flip, the 180 negates their phase. Okay, it just negates their phase. It just flips the whole pancake upside down. So whatever phase that you have now, you have the, I guess, the opposite. And it's not exactly actually a 180, like it's not, in this case, actually, it's not, is it negated? Well, it's reflected about some axis, and really it depends on what axis are you going to apply this 180 that it's going to be ended up with. So it could be negated the phase, or it could be flipped the real part. It really depends on, where what is the angle. But the whole pancake, if you think about it, is just mirrored. And so you get to this point, and then you know that the red spins, those, they were going faster, right? So this is the fastest one, right? That would then go and keep on the same speed. Whereas this is slower, this is slower, this is even slower, more slower, and this one doesn't even move. And this one is actually going the other way. This is the fastest going in the other direction, counterclockwise, right? And this is slower and slower. So what happens is this interesting phenomena, right? All this got to here because it was ahead of everyone. Now it's behind everyone, right? So once you let it persist again, what did I do? Okay. So once you let it persist again, and you'll see it now, this one is ahead, right? And now it flips and it keeps persisting, in the same direction. But because it's faster, then everybody's catching up till you get to a particular time point where suddenly all the spins actually have the same phase. See? Oh, flipped, dephase, 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 and then flip, and then suddenly there's this one time point where actually all the spins rephase, and their signal will go up, and it will go up to the T2 component, right? All the T2 prime component basically disappears because the spins are not phased anymore, dephased anymore, and you rise up to this T2, and then you keep on decaying as T2 star after that again. There's one tiny moment in time where this spread of spins, and actually it doesn't matter what their distribution in space, as long as those spins exhibit constant, constant frequency. So their resonance frequency doesn't change throughout this evolution time. They just keep on going exactly the same speed. Then they'll guarantee to rephase. Okay. So I think what I want to do now is this this is kind of a strange experiment. Okay, if you can put your camera on, I appreciate that. And we're gonna do this experiment by basically rotating our hands somehow. And okay, so I want you to do the following thing, okay? You're gonna raise your hand like that, and then everybody up. Everybody hold their, yeah. And then when I say, and try to hold your left hand, and then we're gonna go counterclockwise, okay? All right, hold on. So when I say go, right, I'm gonna say 3, 2, 1, and then go. And when I say that, you close your eyes actually, and rotate at a speed that you like. And when I say stop, then you just stop at exactly the position that you have. And that position is going to be your face. Okay. So now I want you to then, close your eyes, because that's an important part, because I don't want you to sync, with the rest of the folks. Okay. So I'm going to keep my eyes open, make sure that you are doing the right thing. All right. So when I say 3, 2, 1, again, you're going to rotate your face, and then I'm going to actually time this. And we're going to do it for 5 seconds or so. Okay. So let's see. Timer. Actually, let's do 10 seconds. So it's like even worse. I hope it works.
But wait, Mickey, even now there's not everybody have the same face.
No. I'm gonna adjust. We got, okay. Everybody relax. Relaxation. Have the same phase. Up. Fist up. Fist up. Okay. Close your eyes. 3, 2, 1, go. Two, 1, stop. Okay, so take a look at your position, and you see that everybody's all over the place. So your signal has been defaced. Now what I want you to do is go exactly in the same speed that you went before, but the opposite direction. Okay? All right, close your eyes. 3, 2, 1, go. Three, 2, 1, stop. Okay, hold on. So actually, a lot of you have their fist up, right? A lot of you, some of you don't, okay? And that's good, And the reason that you don't have is because you didn't actually go at exactly the same speed, both forward or backward, because if you would, then you would end up in the same position. But most of you, were up, so we should have gotten some signal refocused, right? So effectively, this is actually what's going on. So the signal that would come back is only if the spins are at a stationary position and it's okay. You can just, we're done. So I would have done this demo slightly different. Normally, if we were in class, we would have get some volunteers, and you'd stand on a line, and then I would ask you to close your eyes and walk forward at whatever speed that you're going. And then when I clap my hand, you're supposed to rotate the other way, and then keep on going exactly the same speed. And what would happen is that everybody would come back to where you start in the same line. And if there was a little bit of a, like if it was not exactly in the same line, that's because somebody is not doing exactly that same thing. And then you'd get some dephasing. Okay. So if If your error field changes over time, then refocusing is not perfect. If your error field does not change over time, then the refocusing is going to be perfect. Okay, does that make sense? Okay, so actually that's an interesting observation, because the fact that if the error field actually changes over time and the refocusing is not perfect, then there will be some dependency of the signal that would actually be, you'll see faster decay effectively than the regular T2 that you would naturally observe. Okay, because you'll still have some dephasing. So that is actually an interesting phenomenon. Now, you don't have to do it only once. You can actually do the whole thing like many times and see many refocusing and effectively be able to see this T1 curve. And here's an example of a multiple spin echo. So you do a 90-degree and then multiple spin echoes after that. And this is the behavior. So first spread, 180, oh, refocus. And then another 180, flip, and then refocus, and then spread. And then another 180, and then refocus. And then another 180, and then refocus. And you can see kind of because of T2 decay, then the whole, the errors start shrinking, right? So this is actually one of the ways that people actually image T2 is through this either multiple refocusing or through repeating the experiment with the 180 just shifted in time. And so you can just see the effective T2 curve. Okay. So this can be also done by multiple refocusing over and over again. Every time you have a 180, then you get some refocusing. Now, an important thing is that any signal due to dephasing, that is some WE as a function of R times time, right? So it's independent. So basically, it's a constant error field that's distributed in space, but the dephasing is just you take this error field and multiply by time, and then that would be pretty much how much phase each component will obtain, right? So if I have some spin at some R position, let's say, actually, let's see this one. So here's a case where you have a dipole field. So you have some source of inhomogeneity, and you have a spin over here. That spin will see a different field than this one sees, and different field than this one sees. Okay, and so the effect will be a very huge. There'll be a strong T2 star, but those spins are seeing exactly the same field, throughout time. And so yes, their phase is going to be WER. That's the phase. That's the I guess frequency at their position times time. And so this will be refocused. However, if you have some error field that changes over time, well, then the refocusing is not going to be perfect, much like we had in the demo that I did with with a fist that's rotating. Okay. So if you have a certain situation, let's say you have a really large blood vessel, remember? You have a very large blood vessel, and you have spins that are diffusing throughout through your evolution. The spins are actually moving through diffusion. Now, because this the effect of this vessel, it's a large vessel, so the way it affects is kind of like it's a spread out effect. And so these spins, while even though they're diffusing, they don't see a significantly different field. And so they'll sample pretty much, I mean, they're very different positions. So T2 star will be large for, if this was a voxel, T2 star would have been huge, right? Huge T2 star effect. However, it will completely refocus if we apply a 180, because those spins will kind of sample exactly, similar field throughout the entire time. But now think of this voxel, and think of a small blood vessel, and now this spins kind of diffuses throughout the time, but now that spin will actually exhibit different field, like it will actually see different field throughout its diffusion. And so if you do that, then you will get time varying dephasing. And that time varying dephasing is not going to be fully refocused. Okay. And it would actually show in a spin echo type of acquisition, it will actually show as a T2 effect. Because your signal will draw, it will rise up, but it will not rise up to the maximum that it could have been if the spin was not diffusing or not seeing those different fields. Okay, so that actually leads to something interesting, because here's an experiment where we expect to see a pure T2, right, phenomena, where we do a spin echo, and then when the echo like refocuses, then we should see a T2. But now the T2 start kind of depending on diffusion, or if it was actually pulsatile, like if the blood was pulsatile and there's some changes in the field homogeneity because of that, that could have caused something to change as well. So, and it also depended on how much these are actually diffusing. So you can actually get to a certain situation where I apply a 90 and a 180 and a 180 and a 180 and a 180. Then next to large vessels, I would actually see my signal kind of decaying, like has an envelope of decay that is, slower than actually tissue which has small vessels in them. Because during this time, the spins actually have time to diffuse, so they will sample a different field, like a time varying field. Whereas next to large vessels, you actually don't see that because they don't have to time to actually sample different fields. So effectively then, if you ask yourself, what is actually T2? T2 is what's called spin-spin relaxation. It's the actually loss of coherence that happens between spins because of spin-spin interaction. But it's really this phenomena that, spins sample different fields throughout their evolution and they lose coherence. So it's really kind of a T2 star effect, but at the microscopic level. But then because things are moving around, then they're sampling of various, different fields that they're, this phenomena cannot be refocused. So what is T2? T2 pretty much is something, it's a relaxation that you cannot refocus with a 180 no matter how you try. And T2 star is a phenomena that you can actually refocus with a 180 if you apply it. Okay, so it's the field that is constant throughout, like it's a field that's inhomogeneous, but it's constant throughout time. Does that make sense? Or any questions up to here?
Can you kind of explain what is it about small blood vessels versus large blood vessels that means that the spins can only sample different fields for small vessels?
Yeah, so let's say, so I drew here kind of like a path, like a random walk, as if these spins are diffusing. So usually spins have, a certain length that they'll go throughout a certain amount of time based on their diffusivity. If it's a small blood vessel, then the field lines are pretty concentrated, as opposed to a large blood vessels where they're not that concentrated. It's like tapers off more slowly. And so if the spins if the diffusion happen over, over in that region, then those spins are sampling a similar field throughout their diffusion. Whereas here they're sampling a very different fields, like the gradient is more significant. And so here they'll, the refocusing is not going to be perfect, where here it's going to be better.
And so how do you know that, for instance, next to a small blood vessel, the faster decay, that it's because of the different fields versus just the decay time for whatever's next to that blood vessel is different? Or do you kind of just know that the spins are the same material?
Well, that's actually very interesting. And so people actually try to model this because people have seen that, for example, that you can actually see functional MRI Remember when we talked about functional MRI, we said, oh, this is a very strong, it's a T2 star effect, right? Because you have, deoxyhemoglobin and oxyhemoglobin, and it's a T2 star effect. So the next to deoxyhemoglobin, the T2 star is stronger than next to oxyhemoglobin. But then people also saw that in a spin acquisition, albeit a smaller effect. And they're starting to wonder, is like, well, what's going on? Why do we see, functional activity due to blood oxygenation in a T2, in a spin echo, right? You shouldn't, because everything should be refocused. And then they noticed that actually next to large vessels, you don't see so much modulation, but actually next, close to capillaries, you see more. And so they realized, hey, actually a spin echo functional MRI experiment is actually more sensitive to the small vessels, while a gradient echo is very sensitive to large vessels. So that's another way of creating that selectivity, doing other experiment that you can try to emphasize, based on the microstructure, what will be, how you emphasize your signal. So one of the ways to do it is through a spin echo. But in general, anything that changes while you have, throughout the evolution, if it changes and it's not constant over time, then that would create a loss of signal. So motion, diffusion, flow that happens during a spin echo readout, it would cause a spin to lose phase and not be able to refocus. Okay. If the motion, by the way, is constant, then they actually will refocus. If the motion is not constant, then they won't. So it's like it's like you have to. So it's really dependent. But diffusion is a really big effect. And so what we see here in many cases is that if you try to measure T2 using what's called a CPMG or a multi-spin echo type of acquisition, if you try to, try to fit a T2, what would be interesting is that if I actually change T, then that would also change, the rate. So if T is short, and I think again, they have a homework question on that, right? Like they have a simulation, right? Oh yeah. So in one of the homeworks, what you'll do is you'll simulate diffusion of spins and apply this type of a pulse sequence. And you'll see that based on the different timing, if T is large, then there's more time for spins to lose coherence, to sample more different fields than if it was very short T. If T was very short, then they don't have time to move much. And so they get refocused. And so the signal lasts for a longer time than when T, this capital T, the distance between those 180s is longer. And what you'll do in the homework is you'll actually simulate that and observe it. So let's leave it to that till you do it. And then if you have more questions, then happy to answer. Okay. All right. So the thing is, as Han actually observed, that you don't have to have a 180 in order to see refocusing. Now, a 180 pulse maximally refocuses the magnetization, but it turns out that even lower one would also have some refocusing. In particular, in 90 degree, will refocus half of your magnetization back. And there's going to be a homework problem on that to derive, but I just want to show you a simulation of kind of how it works. So let me do a new share here over a spin bench simulation. So this is spin bench. And what I'm going to have now is I have a 2 RF pulses here, an 80 and then a 180. Now observe that these are non-ideal RF pulses, so they have a certain length, right? Their length is not infinite, it's not like infinitely small. So that's going to have some consequences. But what I'm going to do now is I'm going to simulate that. And I'm going to simulate using this scatter plot here. You see the scatter plot? So we're going to simulate a lot of isochromat with different frequencies. And this is the important plane. This is the XY plane. And that's the plane that we actually integrate over, and then get our signal, right? Like our signal is really how much transverse components we have. The other ones are a little bit difficult to follow. So in particular, follow this one, okay? And so after the 90, this is what happened. This is immediately after the 90. After the 90, here's the ZX plane. So you can kind of see that the magnetization went from being along the Z direction, now it went into the transverse plane. Okay. But during that time, because you have spins that are with different off resonance frequencies, then you get some spread that already is happening. Once spins are excited, they already start processing. Okay. So you say get a little bit spread, but if you integrate over this, you get a pretty strong signal, right? Like, the transverse component, like the projection onto the X direction, I mean, it's pretty strong. And if you add all these together, you get a very strong signal. Now, after that, you start seeing, oh, they start dephasing and dephasing. And some of them are actually starting to relax, but they're dephasing and dephasing and dephasing and dephasing and dephasing. And then they keep on dephasing, dephasing till we get to the 180, right? As we get to the 180, the whole pancake starts flipping over, right? So the whole pancake flipped over. And in particular, you should look at this, plane. Now it's kind of like, distributed, right? Like almost uniformly around a circle. So there's really shouldn't be any signal whatsoever. And then those spins are now going to keep on processing. And then exactly the same time after, if you have the tau, time tau after the 90, you get the 180, then tau time after the 180, you start seeing, oh, the transverse plane, all these spins are now have approximately the same phase. It's not exactly the same phase because these are not finite 180s. I mean, they're not infinitely, narrow. Actually, if I remove the RF limit and I make the duration of the RF to be infinitely short, then now you would get perfect refocusing. You see, it's perfect refocusing if I removed what I've done, like to make it finite. Now I'm going to enforce those limits, and you can kind of see that, oh, well, we'll have some deviation, but it's it's pretty nice refocusing, I have to say, right? Okay, so now what I'm going to do is I'm going to start sweeping from a 180. I'm going to start reducing the flip angle of the refocusing pulse down to 0. Okay, so at 180 we get the maximum, right? That's the most refocusing. But now I'm going to do a 140. I mean, this is still pretty refocused, right? Even at 140, you get a significant portion of your magnetization being refocused. Now I'm going to go to 100, and this is what happens when you're at 90. Okay, you see that most of the spins are on the left-hand side of the plane. So if you actually integrate on them, you'll still have a signal. How much signal is it? Because this is a circle and you integrate over, it actually ends up being half. Okay, so if you actually integrate over the X component, right? Like if the Y component cancels, right, on both sides, but the X component adds. And so you'll have a significant amount of signal. And now if I actually reduce it further, then you start seeing, oh, now I have spins on the right-hand side. So yeah, when I integrate, I still have some signal, but that signal is lower. And then when I get to a very small flip angle, well, now I don't get any signal, almost very little signal. So you kind of see how those spins kind of move and refocus completely when it's a full 180. When it's a 90, it's half, and then below that, it's less than half. Okay. And of course, you can see it more nicely if I actually do a perfect 180. So let me do that. So now it's a perfect, and let's put a 180 here. Yeah, so this is the perfect refocusing. And then if I pick, you know, like a 150, look how nicely a 150 refocuses. Now, why would somebody want to use a 150 instead of a 180? How much less power a 150 is compared to a 180?
Would it be because of SAR?
Yeah, SAR can be a really issue. And so putting a lot of 180s, you know, could be a real problem. But as it turns out, 150 actually refocuses 90-something% of the magnetization. So you reduce SAR significantly because SAR is actually, let me mute some folks here. Yeah. Okay. SAR is actually quadratic, goes quadratic with the RF amplitude, whereas the refocusing amount of refocusing doesn't. So there is actually a really nice sweet spot where we can reduce the amplitude, not reduce so much of the refocusing, but then significantly save on SAR.
I have a question.
Yeah.
Over here on the top left, your graph that says magnitude.
Over here, yeah.
When you set your parameters where you said you got no signal, that graph still had signal, so I got confused.
What do you mean? No, so this is the actual magnitude of the MXY component versus frequency. So just ignore this one because it doesn't integrate over the, like it basically shows each one of these arrows, like each one of these arrows represent a point over here. So you see that a lot of them being excited, right? If I do a 90, then you see that only like some of them are being excited and some of them are not. Right, some frequencies, some off resonance frequencies will produce a large signal and some would not. And this is the distribution of them. Okay.
Nikki,
Yeah.
I have a question too. So would another reason for flipping less than 180 be to speed things up?
Yeah, it could be too, because of the amplitude limitation, sometimes you have to spread your RF to be longer. And so if you want to save some time then and make your RF pulses shorter, then you can do also less than 180. That's another, that's another good reason. Yeah. Thanks for that. Okay. So this can be easily derived, by the way, and in the homework, you'll derive actually the 90-90. Okay. Okay, so so these are the two examples using SpinBench that I showed you before. By the way, I highly recommend for those of you who have Macs to download SpinBench. It's a really nice pulse sequence design kind of thing, and also simulation that you can play with. But you do need a Mac for it, unfortunately. There's other simulation tools for Windows, but they're not as slick as nice as this one. And one advantage actually of doing this pulse sequence programming is that we have a real-time system that installed on the G3T that actually you can take a SpinBench sequence and just run it on the scanner, which is nice. So if anybody wants to do a project in programming in SpinBench and then going to the scanner and applying it to test some sequence, that's a great project. So you can implement a pulse sequence using this, and then go ahead and run it on the scanner. It's pretty cool. Okay, now I mentioned that, you can get a spin echo with low flip angle, but really what happening is that, it's kind of like a complex behavior, right? Like some spins will refocus and some will not, and so on and so forth. So there's a really nice derivation that you can come up with that if you apply a sequence of 2 pulses, or actually, a sequence of 2 pulses, then each pulse or the result of the second RF pulse can be decomposed into several components, okay? And you can track each one of these components and see kind of how they change. And so the first component is a pass-through. It's basically some spins that appear to not see the RF, okay? They just keep on behaving as they would, okay? So they're not seeing the RF. The other component is the refocus component, is spins that exhibit an inversion of phase, and now they're starting to refocus back. A third one is what's called parasitic excitation. I mean, you're excited, you're applying some RF, but let's say there is some MZ component, and now you're applying an RF, so it actually creates some excitation. So there's new MXY that's being created at the second RF. And then the third one is taking some MXY component that was already in the MXY and then moving it back into the MZ component, okay? So there's 4 components here that you can track. And so depending on what flip angle you do, some of these would be degenerate, so they basically not exist. For example, if you do a perfect 180, then this doesn't exist. This is the only component that's left. This doesn't exist, and this doesn't exist if you do a perfect 180. But if it's not a perfect 180, then you will get some of the other components too. Okay. So effectively, if I have a sequence of alpha and then another alpha after that, and this is tau time before the alpha, and this is tau time after the alpha, if I want to know what is the magnetization at this time point, right? I want to know what's going on here. Well, what is actually going on? Well, I had some magnetization that was some M0. Then I apply a rotation. Let me see if that's the order. Yeah. So then an alpha Rx. Yeah. So this is a rotation around the x-axis. So this is excitation. So excitation by alpha. So rotation around the x-axis by alpha, and that creates some MXY component, right? Okay. Just ignore this part for a second. This is immediately after. This is the magnetization at this time point, right? Rx, like rotation matrix with respect to the x-axis, so around the x-axis, and you apply an alpha rotation. Does that make sense? Okay. So then what happens after that? Well, after that, there's free induction decay, right? Like there's basically just evolution and precession. We're ignoring T2. We're ignoring T2 decay. So there's just free precession during that time. Free precession happens about the z-axis. So there is some rotation about the z-axis. How much rotation? Well, that depends on the frequency of rotation, W sub E, and the length of time. Okay. So again, alpha excitation followed a free precession that is, you end up with a certain amount of rotation that depends on how much field variation you have and how much time you've waited. Okay. After that, you apply another rotation around the x-axis by alpha. And then finally, another time of free precession. Okay, around the z-axis. So basically, I described it using 1, 2, 3, 4 rotation matrices. Okay. All right. So for 90 degrees, if you actually do this derivation and follow the magnetization, this is what you get for 90. Okay, I'm not going to derive this because that's your homework problem. Okay, but you're going to end up, basically you're going to do this and then you're going to multiply and then you know, that's what you're going to end up with. So here's a solution for your homework problem, but you need to derive it. Okay, so you get this component, right? So you get M0 multiplied by I sine a square omega E times tau, and then M0 times sinus omega E 2 tau, and then multiply by half, okay? Actually, yeah, so that's it. So, so this is the MXY component, right? That is dependent on where you are in space, because the omega E is the function of space. So if I integrate over the entire thing, that would then produce me, you know, what is actually the signal within that voxel if I integrate over a voxel. Okay, then this is what I would get. Now, when you integrate, what do we integrate over? Well, I'm going to integrate over all possible off resonances, right? I'm going to assume that the off resonance is, you know, is uniformly distributed. I'm just going to integrate over all possible off resonances. And what you could see here that when you integrate over this, what is this really? This is an off resonance that evolved for 2 taus, right? So effectively, this is what's called the through component, the pass-through component, because it's off resonances that evolved for twice the time. It didn't really see the alpha kind of, because it just continued to process during that entire time somehow. This component over here is squared. Okay, so when you integrate over that, what is the integration over a sine with all possible flip, you know, all possible phases? What is the result of that integration?
0.
0, right? Because basically whatever is positive will cancel with negative and so on and so forth. So basically this results in nothing, producing no signal. The pass-through component results in nothing. It's dephased. What about when you integrate over this? Because it's square, then it's only positive, right? So when you integrate over it, it's actually going to end up being half. So integrating over sine square results in half. So the signal that you're going to get is pretty much half J, right? Which is kind of what we get. Does that make sense? Okay. So in general, if you have any series of alpha and alpha, it can be decomposed into, I mean, you can kind of track through all the terms. And then what I'm going to do after you track all the terms, what you do is you're going to collect. I'm going to collect all the squares together, I'm going to collect all the cosine with a single WE altogether. And I'm going to collect also the ones that have 2 W sub E times tau altogether. Okay. And you end up with A1 times cosine 2 of that, A2 times sine over that, and then B1 times cosine square, and so on and so forth. The part that has actually the cosine square is the part that if you integrate over will end up with a signal. So this is actually what we call the refocus part, because it's squared. So this is the refocus magnetization. This one we call pass through because it's actually seen 2 phases of I guess dephasing, right? It dephased by 2 taus. And this part over here only seen, you know, dephasing over a single period, like a single tau, right? Does that make sense? So this part is probably some magnetization that was not excited and was only excited by this alpha. So it's seeing only this part. This magnetization was excited over here and then seen twice as that. And then this magnetization seen these two and was refocused when you ended up over here. Okay. So basically, no matter what alpha is, you can always decompose it into this and then figure out what is this component. When it's when alpha is 180, then these end up being 0. And you only have fully refocused, so your entire signal. So obviously when you integrate over that, then you get 1. Okay. Does that make sense? So you can come up with this derivation and solve it. But here's actually a really useful way of thinking about things. Okay. And this is called what's called a phase graph. Okay. So in a phase graph, what you do is you try to plot what will be the phase evolution of spins when you apply these RF pulses. So this is time, and this is phase. Okay. And this phase graphs allows you to track all these components that are being generated. Okay. So the first time you apply an alpha, then that creates some MXY that immediately starts dephasing with a constant phase, right? Some WE times tau. So it starts dephasing with a constant phase. Now, when another alpha is being applied, well, what happens is a few things happen. One is that there is going to be some component is going to be refocused. That means that this, some component of this is going to be flipped in phase. If it was a full 180, then the entire component would have been flipped. And so it's going to have a negative phase. There's another component that is not affected by this alpha. Again, this is a model, right? But basically describes those terms that I showed you before. That it just keeps on dephasing. Okay, some other spins, you know, they keep on dephasing. And this alpha may also create an excitation, a new excitation. It's called parasitic excitation because we don't mean to create it, but because it's not a 180, it is creating it. So, and that magnetization did not see the first RF. It's new magnetization being created. So it starts dephasing exactly at this point. And finally, there is another component that basically it's magnetization that saw this phase, but now it's stored in the longitudinal component. It went back into the longitudinal direction. And so it's stored in MZ. Okay. And basically it doesn't accrue any phase because it's in MZ. Okay. So here's what happens. So this alpha then, after we apply this alpha, we can track what's going on and let all these echoes that are generated or all this magnetization, we can track what their phase are. But what's nice about it is that we can see that immediately, you know, after, if this is tau time, then after tau time, the magnetization that was flipped in phase is going to be refocused and an echo is going to be generated. And at this time point, you have some component that's seen tau dephasing and another component that saw 2 tau dephasing, right? And so this is very similar to the tau dephasing, 2 tau dephasing and tau dephasing. Okay. So this is a really nice way to track it. And you know what? The cool thing about it is that if I now apply another alpha over here, actually, let me apply, let's say I apply an alpha over here, then what would happen is I can actually now track what's going on. So this will create some refocusing. There's another one that's generated over here. And so now I'm going to track this here. And then this one is also going to be refocused. And I'm going to track over here. So effectively, after applying the third alpha, I will get actually refocusing at this time point, but actually I would also get a refocusing at this time point. Because this alpha would refocus also, magnetization that took, that was parasitically excited. Actually, I will get another one because this continues on too. And then that would end up also crossing here. So I will get 1, 2, 3 echoes after the third alpha. This alpha will refocus magnetization that was excited in the beginning, that just was a pass-through. This alpha would also refocus new magnetization that was created by this one, right? And so on and so forth. So there's actually many echoes that are going to be. And the nice thing about this phase diagram, it allows you to actually track at what time points these echoes are going to occur. And here's an example where you have alpha, alpha, and alpha, and you can see how many echoes are now being created after you do all of that. And how much magnetization is going to be stored, and so on and so forth. So it's allowing you kind of to put an order to what's actually going on. And you can see it's actually quite complex, right? And each of these echoes, exhibit different T2 decay and, different diffusion may see. So, they're weighted by a lot of things. So it's really, really fascinating. The fact that you're applying a series of alphas, you're creating all those echoes that, are out there. And in the homework, in one of the homework that you'll have, in simulation, you're going to apply 10 times alphas, and then you can kind of see, oh, wow, after that, there's a lot of echoes being created. Like you'll see the magnetization kind of come back up and then go down and up again, even though you're not applying anything anymore. Like you do applying, 9 alphas. And then after that, you just wait for the FID and you start, popping out, because of that. Now, the limitation of this phase graph is that you really, well, when the echoes are occurring, you actually don't know how much they are, how much each component is. And so there's actually, if you think about it, each component has a different magnitude and a different phase. And so each echo consists of contribution of many, many different pathways, right? They could have been stored and excited and, evolved, and also, this could be lots of combinations. And one thing you could do is that you can actually track what their magnitude and phase is and calculate it for each echo. And this is called a extended phase graph, which then allows you to really see what's going on within each echoes. And so there's a paper and a document by Matthias Wiggle of how to perform this analysis, and it's called extended phase graph. And if you want to do a project of implementing an extended phase graph algorithm in order to kind of simulate what's going on when you apply many RF pulses and gradients, then that could be another interesting project. Okay, but that's beyond kind of what we're going to cover in class. Right? But obviously, this could be an issue. For example, if you're, let's say, doing a sequence where you apply an RF and then you do imaging, and then you don't wait till everything decays, and you apply another 90 degree, and then do an imaging, there could be this parasitic echo that pops out. It refocuses usually during some of those TRs, and it could be different. And so that's going to result in artifacts in your image because you're not counting them, like they're not supposed to be there, right? Like you're not maybe modeling them. So that could be an issue. So if you're doing a short, like many repetition of alpha followed by an imaging, alpha imaging, then that could be a problem if you don't track exactly where those echoes are being generated. So that could be an issue. Okay. We'll go more on it when we talk about steady state sequences. Okay, and we'll get to that I think soon. Some of it is actually not in the book, but we're still going to cover that because I think it's super important to see. Now, how important is it? Super. I said super. Super important. Yeah. I gave you the solution. All right. Okay, so now the question is, if we want to create a sequence using spin echoes in a let's say 2DFT acquisition, how do we do that? Right? Because the problem is we do a 90 degree, like a 90, and then we do all the phasing coding and all that stuff in the readout, and then we get pretty much T2 star decay till we get to the echo, right? But what if we want to image a pure T2 and we want things to refocus? How do we leverage that spin echo? Okay, so this is what we're going to talk about right now. Okay, so effectively, spin echo negates the phase. Okay, it flips the phase. So how do we incorporate that in a pulse sequence? Okay, so effectively MXY, like your magnetization in an imaging sequence, MXY as a function of space and time is MXY as a function of space at time 0 multiplied by whatever gradient encoding we do, right? E to the minus I 2 pi kx times x plus ky times y, right? We've seen that's the effect of the gradients, right? That's the effect of the gradients. The question is, what's going on when you apply a 180? Okay, so what happens is that it will negate your phase. So your phase, instead of being negative, it will change to be positive if you apply a 180. What does it mean to have a positive, here? That also means that I basically can negate each one of these, right? So effectively if I reach a certain kx and I reach a certain ky, the fact that I do a 180 basically negates them. So if I have some sequence and I end up at this point in K space, the fact that I'm putting a 180, then my K space jumps and lands on the opposite side. It's a way to jump in K space. Like normally K space trajectories, right? They have to be continuous and connected. But the 180 spin echo takes that and flips it immediately to the other direction. Okay, that's really is the effect on imaging. So now you can think of, okay, well, what, you can think of actually, what to do then in terms of incorporating that into a sequence. So here's a regular 2DFT, and this is called gradient recalled echo. Now, why is this a gradient recalled echo? Why do we call it an echo, actually? Anybody has an idea? Like, why did we call it the spin echo? A spin echo was, you do a 90 and you do a 180, right? And then the signal after the 90 is, has a decay. And then after the 180, what happened is that the signal rises up back. And then we call this an echo, right? Okay. So what happens when you actually do an imaging? Here you excite, so you get some signal, and then you go out in K space, right? Let's ignore the phasing code right now. So let's say we are in K space, and then we're going out in K space, right? Using this, we go negative in K space, and then we traverse K space from left to right, right? So we go from here to here. What's our signal? Well, during this time, our signal decays because of the gradient. We go out in K space. The center of K space is the highest signal, remember that. And so our signal, as we move out in K space, the signal goes down. And then when we go back to the center of K space, our signal goes back up and then decays again. So that's kind of similar, right? But this coming back is just because the gradient area here is exactly the same as the gradient area here. So they cancel. Whatever dephasing this gradient introduced, this refocuses it back. So this is what it's called, gradient recalled echo, or GRE, gradient recalled echo. Has nothing to do with spin echo or T2 star. This is just the dephasing that happens because of the gradient, and then rephasing because the gradients are being flipped. Okay. All right. So this is a gradient recalled echo sequence. And effectively, we get an echo at time TE exactly when this part rewinds this part. Okay. So this is the time where you get the maximum signal. And this is what's called echo time. And this is the TE, the time, the echo time. Okay, so how do we convert that into a spin echo? So first of all, we want, whenever we cross the center of K-space, that is actually the time where we want the spin echo to occur, because we want the maximum signal to occur because of the gradient as well as because of the spin echo. So we want to align both of them to be at the same time. So that means I need to put the spin echo kind of at half the TE. Now, obviously, this cannot happen here, because if I just add a 180 over here, right, then it would be selective because there's a gradient on here and this is on. So, you know, that's not going to work out because the RF will be while gradients are happening. And so that's not going to work. Okay. So the other thing is that these, you know, you're applying some inhomogeneity. Now there's a 180 that refocuses that inhomogeneity. So it's going to be a mess. So what we could do is basically, we need to push the whole thing. So the disadvantage of a spin echo is that actually the echo time has to be longer. TE in spin echo sequences is always longer because you have to put time for the 180, and also you have to wait TE before and TE after such that you can align the gradient echo and the spin echo. So here's the situation. And this is a trivial adaptation of the first thing. Anybody has an idea? What I did is I put, this is the slice select 90, and then I put a 180 over here. Okay. Now this 180, this is non-selective in this case, but that's not a problem because if it's a perfect 180, then it would invert all the, like any pancake that's being flipped is going to flip the pancake. And whatever spins that are not in the same slice are just going to be inverted and not going to produce MXY. Okay, they're just going to be inverted. Okay, so that should kind of work. Okay, of course I can make that into selective, but I'm just ignore that for a second. Okay, so what I want to align the readout. The middle of the readout, I want to align with the spin echo. The spin echo happens at this time. So effectively, my readout window, GX, needs to be aligned along that time. Okay, that's my readout window, right? And then I need a pre-winder for that readout. So I can actually put that pre-winder over here. Okay. And this whole thing, I can basically squeeze to the left till it hits the 180, right? Like I cannot overlap them. Does that make sense? So I cannot overlap this pre-winder with a 180. So that length, you know, that increases the echo time a little bit because of that. Okay. So, okay. And then I can also add phasing codes. So let's say I'm going to add phasing codes over here. So these are the phasing codes. Okay, so now I've got myself a spin echo and a gradient echo actually at the same time. Woohoo! This is a spin echo sequence. And this turns out to be minimum motion artifact. Now, why is that a minimum motion artifact? Well, if there is a motion that occurred, let's say, between the excitation and the readout, then the effect was going to be really minimal over here, as opposed to the next situation where I'm going to show you the next one. Okay. So this is one extension, but there's a problem here, right? These have a certain time length and they push the echo time to be longer. What if I want to make the echo time shorter, like the minimum echo time? There's all this dead time before the 180. Is there a way for me to move these before the 180? If I can move them before the 180, then I can move the readout to be as close as possible to the 180, right? And make the echo time shorter. And that could be an issue, definitely, if I have a very fast T2 decay, right? That could be a significant issue. So can I do that? Is it possible? Any suggestions? So let's put this 180, right? And I'm going to start the readout over here. Okay, so now my echo time is shorter. Okay, I basically was able to move this closer. Even though I didn't draw it exactly perfectly, but just imagine that they're the same, okay? Okay, so I need to do that. So let's put the, actually, what I could do is I could probably overlap, the pre-winder with the slice select, right? Because there's no acquisition with the slice select refocusing. So I could, put this over here, right? And I could put a phasing code during this time, right? Is that going to work? Let's see. Let's see where we are in K-space, okay? So immediately after excitation, we're in the center of K-space, right? And this is KX. And this is KY. Okay. All right, so then I go positive in KY and negative in KX, right? Okay. So effectively, I'm gonna go to here, right? Like before. Okay, then I reach the 180. Now, what does the 180 does? It flips K-space, right? Like it negates K-space, right? So it basically, K-space now jumps to this point. And now I have a positive readout. So now I'm going to be reading in this direction. Uh-oh. That's a problem, right? So what do I need to do actually for things to work out? I can hear if you want to say something.
Flip the sign of GY and GX.
That's right. Yeah. So let's see if I can do that. I need to do a lot of undos. That's the problem with this software. Sorry about that. Okay. All right. So what if I flip? So that's weird, right? That's the pre-winder. And then the first phasing code. The first phasing code is going to be in this direction, right? And so now what I'm doing is I'm actually traveling in this direction and then jumping to here, right? And then the readout is gonna have me read this line. Woo! And then the next one is going to be a phasing code with a little bit less, which gonna read this line. And then another phasing code, and then another phasing code, and then another phasing code, right? And so on and so forth. This is minimum, T, but it's a little bit more sensitive to motion because the phasing code and the readout prewinder could be tens of milliseconds apart. And so those could be encoded where spins are in one position, but then during the readout, it might be in a slightly different position. And so that can cause artifacts that are very common in spin echo. Okay, in particular when there's flow. So it's more sensitive to flow, but this is a shorter. Is this what they're going to implement in the lab, right? Kind of.
Yeah.
In the lab, they're actually you're also doing slice selection on the spin echo.
Yeah.
Okay. Now, there's another issue with this. What if the 180 over here is not perfect? If this is not a perfect 180, what's going to happen?
You get XY component emissions.
Yeah, I mean, so there is some components that are going to basically be refocused, right?
Mhm.
Yeah, basically, this is going to refocus whatever's been excited here. If it's not a perfect 180, there's also another component that's going to keep dephasing, right? But that's not an issue because when it reaches here, it's going to have a lot of phase. So it's going to die, right? Like we're not going to see a signal. But there is actually a component that's going to be actually excited here. Just imagine if it's not a pure 180 and this is not slice selective, right? So it's actually going to excite stuff outside of the slice, right? And it's going to create MXY component in the entire volume. It's actually significant. Even if this 179 degrees is going to excite 1 degree everywhere in the volume except, in the slice, right? So that is going to be excited here. Now, is that a problem? Well, let's actually track things, what's going on. So here's the 180, right? And let's try to do what's called a track the phase of each component, right? So there's a component that's created over here that's going to start, evolving phase, right? Till we reach this one, this 180. I'm going to do a phase graph now. Okay, so we reach the 180, and then some of it is going to be negated and refocused. And there's another component here that's going to be generated and excited. Okay. So, and then there's another one that's going to continue. So this is going to dephase. This is going to be refocused. And that's actually our spin echo. But there's a new component that is just generated by that, right? Now, here's the thing. Your GX and your GY, they happened here. So this component sees these, right? This component, the refocused one, also seeing this. Okay. This component actually didn't see the 180. So it's K-space that you're going to read. This component, when you're going to read now the K-space, this is GX, right? when you're going to read K-space, this component has not seen the 180. So that actually is going to go, so it's basically going to read out this K-space, right? This one is going to read here. So it basically reads no signal whatsoever, right? This component over here that was refocused, well, then that is going to jump to here and we're going to read this line. So yes, so we're reading the entire K-space for this component. But what about the component here that was just generated at the 180? It sees this gradient, but it never saw these gradients. So for this component that was generated over here, it's like we're going from the center of K-space and just reading positive. So we're getting like 3 images at the same time. One of them produces no signal. That's the pass-through. The refocus one produces the right signal. And then this parasitic excitation that was created, the 180, sees this gradient, but it doesn't see the phasing codes. So every phasing code that you do, you collect the center of K-space again and again and again. So it's pretty strong signal. So effectively, if you actually fill in the matrix, right? Like you're thinking, when you're doing the recon, you're thinking that you're actually going in K-space over here, but you're actually collecting this signal. And so you get a constant signal, a constant signal, a constant, the same signal over and over again. And then you're doing a Fourier transform. What happens if you have a constant signal all the time in the Y direction and you apply a Fourier transform? What happens if something is constant in Y?
A delta.
Right. It's a delta in Y, but because it sees the X gradient, so it's a little bit spread out in X. So what you'll get is an image with an artifact, a line artifact in the middle of the image. You'll see that in the lab. In the lab, you'll actually do this and you'll see. Did you see this? Folks that seen the lab, right? You've seen this artifact. So what you do instead is, in order to mitigate with this, you can do plus minus modulations. When you do an even phasing code, you do a plus 90. When you do an odd phasing code, you do a minus 90. Sorry, not plus 180 and then a minus 180. Now, the fact that you do a plus 180 or a minus 180 doesn't affect the refocusing. The refocusing is exactly the same. It doesn't matter if you do it, you flip the pancake this way or flip the pancake the other way. It's still flipped. It has exactly the same result. But the component that's generated at the 180 is going to have opposite, alternating phase. And what happens if you have a plus minus 1 modulation?
It'll shift.
Shifts by half the field of view. Yeah, plus minus 1 modulation shifts by half the field of view. So now if you do this, your artifact will shift to the edge of the image. And this is one way to mitigate with that. And that's what you'll do in the lab also. And this is actually a result of a clinical scan using a Philips scanner, spin echo sequence. And you see this artifact that's like at the edge of the image? That's exactly this. Naturally, this would have occurred in the middle if we didn't chop the 180. It's called chopping or phase cycling the 180. But once you phase cycle the 180 or chop it, then the artifact actually goes to the edge of the image, and that's not a problem anymore. Okay, so that's one way to mitigate with that. There's actually other ways to mitigate with this, and I'll mention, I'll talk to that, but on Thursday. Okay, on Thursday we'll talk about actually how do we do. How do we do multi-slice? Because one of the issues is when we do 180, of a single slice, it doesn't invert the other slices. So, well, now we have to wait for them to completely recover, right, before we can do anything. So that's an issue. So we probably want to do a slice selective 180. And so we're going to talk about that next time, right? But hopefully now you'll understand both the lab and the homework, because we have exactly the same homework that you're going to derive this. And so you're going to see this twice. And hopefully, you'll get kind of in your head kind of like the notion of what is a parasitic excitation, that doesn't see all the phasing codes, and like what happens to it and how to mitigate with that. So imaging is a lot about managing those echoes where they occur and then throwing them into places where we don't care. Right? This is an echo that's generated. Right? Is a spin. It's actually a gradient echo. It's a gradient echo that's generated that we don't want. Right? It's a gradient echo that we don't want, because it is refocused by the gradient at this time point. So we need to get rid of it somehow. So one of the ways to do it is by chopping. Right? So hopefully that's been a little bit clear. You'll see this in the lab again in the homework. And again, next time I said we're going to talk about multi-slice. And we're going to keep on moving then into other type of image considerations, like other artifacts, for example, gradient nonlinearities, Maxwell terms that we're going to get to them, and even B1 inhomogeneities next time. All right. So I think I'm, as usual, a little bit over time, but I think we covered most of the things that I wanted to. And now you're ready to go through the lab, and hopefully you're excited because you're going to be able to see this effect, which is pretty nice, I thought. Right? We had to optimize that sequence so you can actually see this effect for a number of reasons. Bye, everyone. Come to my office hours, okay?